In this video, what is a bond? We're going to start thinking about how does a molecule show up in 3D space. So we know that molecules have 3D shape. When we think about pharmacological molecules such as an antidepressant or a histamine blocker, many of these proteins or many of these small molecules, meaning a compound, fits into a protein pocket. And so when we think about a protein that could look something like this, what we're going to end up having is a small molecule that fits in this pocket. And so both of these things have 3D space, or both have a 3D shape. So when we think about 3D shape, it doesn't really matter what it is, but it has it. So over the next several videos in group 10 and group 11, we're going to look at 4 models that provide insight into how molecules are connected. We're going to start with Lewis structures, then we're going to go to VSEPR or VESPR, then we'll talk about hybridization and MO theory. Essentially, each of these models can only go so far. At some point, it begins to collapse. When it starts to collapse, a new model was developed, and we will look at each of these independently. So in order to think about how a bond or how things look in 3D space, we need to think about what is a bond. So a bond is composed of 2 shared electrons along the internuclear axis. Essentially, it says if we have atom A and atom B, the 2 electrons will be here along this axis. So this is the internuclear axis. And so in general, there are 3 different types or classes of bonds. So let's look at those individually. So first, we have an ionic bond, and this is between a nonmetal and a metal. And so in most, if not all ionic bonds, electrons are transferred. Which basically means that we have an anion and a cation that are oppositely charged elements that are attracted to one another. So the cation and anion are attracted to one another. So the most different type from an ionic bond is a covalent bond. So a covalent bond is between two nonmetals. And so the electrons are shared. Now, you may have heard about something called a polar bond or looked at a different video in this series where we look at polar bonds. But whether they are shared equally or unequally, they are shared. And so in this case, both elements share electrons to achieve octet. Where in an ionic bond, the electrons are transferred. So both the cation and the anion will have octet. However, they won't share any of the electrons. So the last classification is metallic bonds, and these are between metals. So we can think about this, whether it's a metal complex, meaning more than one type of metal, or a single metal, such as a chunk of iron or something else. So the electrons are shared between all elements. And so the sharing creates an electron C. And so this electron C allows the electrons to move back and forth, which is part of how metallic compounds can, but not always, conduct electricity. So these are the 3 main types of bonds. And so a bond is when 2 electrons are shared between 2 elements. And these are going to be created through our valence electrons. Valence electrons are electrons in the outermost shell. It's really important, but they're only the s&p orbitals. And so these valence electrons are the same and predictable based on location for elements. So if we were to look at the periodic table, the number of valence electrons, is 1, 2, 3, 4, 5, 6, 7, 8, where the noble gases have a full octet. And so we can draw Lewis dot structures to identify the Lewis dots. So let's look at these for all of the elements in the second period. So for lithium, it has 1 valence electron. So you draw it with a single dot. Beryllium has 2 valence electrons. And these 2 electrons want to be as far apart both in physical space and in our Lewis dot structure. So boron has 3, and they also want to be as far apart as possible. Now, when you draw boron, one side is free, and it doesn't matter which side, as long as 3 of the 4 sides have a single dot. So you may have noticed that I'm drawing essentially a box. So the Lewis dot structures of the valence electrons show us that there are 8 different places where the electrons can go. And so we're using this arrangement where your atom is inside and those electrons are distributed around. So up next is carbon, which has 4 valence electrons. And those 4 valence electrons can be found 1 on each of the 4 sides. So I'm going to draw a little squiggle here between these so we can clearly distinguish those. So up next is nitrogen. It has 5 valence electrons, and 2 of them, so if we put our 4 around, this last one can go on any of the sides. So I'm going to put it on the top one. But you could have selected any of the 4 sides as long as you have 3 lone electrons in a single pair. So we have oxygen with 6 valence electrons, fluorine with 7 valence electrons, and neon with 8. So for oxygen, we have 1, 2, 3, 4, 5, 6. It's really important that the 2 single electrons are on opposite sides, because this will help us as we build our models into 3D space. Fluorine has 7, so we have 1, 2, 3, 4, 5, 6, 7. And that lone electron can be on any of the 4 sides as long as you just have 1. And neon has 8, and we can see those annotated this way. And my dots are quite large. I want to make sure you can see them on the screen. And so the octet rule, or the rule of octet, is when there are 8 valence electrons around any element. And so as we start to look at bonds in depth, what we'll see is that these 8 electrons can be owned or shared between different compounds. And so 8 is octet, and octet will be the goal, except for hydrogen and helium, where the outermost shell 1s can only have 2 electrons. So their version of quote unquote octet or duet only contains 2 electrons. So in the upcoming videos, we'll look at how to combine these in order to make bonds.